In this video, we're going to talk about a property of motion that many of you are probably fairly familiar with, and that is the property of momentum. Specifically, in this video, we're going to talk about the conservation of momentum. So not only how you can calculate momentum, but how momentum can be compared before and after some sort of event that changes the motion of the object or objects at play. Before we can really get into the numbers, though, let's define momentum. Back in our forces unit, we talked a little bit about this idea of Newton's laws. Well, Newton's first law was stating that an object in motion stays in motion, object at rest stays at rest, unless there's some sort of unbalanced force to change that motion. And one of the ways we described it was the law of inertia. Inertia being an object's tendency to continue doing whatever it's doing, an object's tendency to resist a change in its motion. Well, momentum is basically just the motion part. It's the inertia in motion. So if an object is in motion, momentum states an object wants to continue in motion. And what's useful about momentum, rather than just inertia, is we can quantify momentum. So in order to quantify it, we need to know the different properties that are players in this conversation. If I have a semi-truck and a Tonka truck, semi-truck being about 20,000 kilograms and the Tonka truck being 2 kilograms, we can figure out which one has more momentum. If they are moving the same velocity, then the velocity isn't a factor. It's just the mass. Well, this semi-truck is going to be a lot harder to stop than the Tonka truck because it has much more mass. So we say that the semi-truck has far more momentum because of that factor of mass. Well, if we have two Tonka trucks now instead, we've got a 2 kilogram and a 2 kilogram. Now we can look at which one has more momentum based on velocity. We've got 10 meters per second for this one on the bottom and a whopping 35 meters per second. So that's really flying on the one on the top. Well, that one's going to have a lot more momentum because it has far more velocity. It's a lot harder to stop because of how fast it's moving. So now we know that mass and velocity just intuitively are going to increase an object's momentum. Well, we can quantify that using the momentum equation that factors in both the mass times the velocity. In our equation, we're going to use lowercase m for the mass, a lowercase v for the velocity, and our symbol for momentum is, get this, lowercase p. Not something that you would intuitively necessarily think of. It's for the silent p in the word momentum, silent and invisible. So p is going to be our symbol. You'll just get used to it. For our equation units, our mass is going to be measured in kilograms. Our velocity is measured in meters per second. Now, in our previous conversations, we've talked about force and we've talked about work and power and energy. And all of those were derived units that we didn't have this string of fundamentals. Instead, we said force is newtons, energy is joules. Well, momentum doesn't have a derived unit. Instead, we are just going to keep all the units here and say that momentum is measured in kilograms times meters per second. So kg m seconds to the minus 1. If you ever forget, you can just plug in the units to this equation, mass times velocity, and what it gives you is your unit of momentum. So in your data booklet, you will see this equation here. It's up at the very top of subtopic 2.4. P is equal to mv. There's our P again, indicating our momentum. So in this video, we're going to talk about 3 primary events that could happen that you could analyze the momentum of. And you need to be familiar with these 3 because really all the examples that we'll see will fall into one of these 3 situations. And the first one I'm going to call the explosion. This isn't an official IB terminology. It just helps me keep them straight. So explosion doesn't necessarily have to have some sort of explosive here. It can be as simple as you standing on a skateboard, as we have all done, holding a bowling ball, wearing your top hat, and then chucking that bowling ball at someone. Well, the bowling ball is going to move off in one way, and you are going to start rolling backward in the opposite direction. That is our explosion. We have something that was one unified thing, you and the bowling ball together, that splits up into more than one thing. The bowling ball separate, and then you separate. Our second example is going to be called the hit and bounce. Here we have a bowling ball rolling and it hits the skateboard. It bounces, so it has its own velocity final. So does the skateboarder. So they are two objects that hit, and there are still two objects with their own unique velocities. So that is our hit and bounce. And our last example is a hit and stick. So say you're standing on your skateboard with your top hat on, and somebody's like, here, catch, and throws you a bowling ball, and you catch it, and then like a boss, roll off the screen slowly, holding that bowling ball. That is a hit and stick. You have two objects individually that have their own momentum, own velocity, and then end up with one unified object that has a final velocity together. So you need to be able to parse out which of these three scenarios you have. Is it an explosion? Is it a hit and bounce? And is it a hit and stick? Now, for all of these three scenarios, we know that the conservation of momentum is always true. Conservation of momentum, similar to the conservation of energy, basically just says that the total is constant before and after. So the total momentum of this system is constant. It doesn't mean that the momentum of the bowling ball is always the same. It means that the momentum of the bowling ball plus the skateboarder is always the same. So you have to factor in all of the objects in that system, add them together, sometimes keeping in mind the direction. Momentum is a vector quantity, to factor in what the total is going to be. So Newton's third law is one that we haven't talked about too much yet until this point. Newton's first law we talked about even at the beginning of this video, introducing momentum. We've talked about Newton's second law quite a bit as well. Force is equal to mass times acceleration, or truly an unbalanced force causes a change in an object's rate of change in momentum. But really we use F equals ma most of the time, basically saying that a larger force produces a larger acceleration. Well, Newton's third law is for every action there is an equal and opposite reaction. You're probably familiar with that one as well. It's kind of got this catchphrase to it. Well, there are some examples that I think are important to go over and just remind ourselves what that means. So imagine yourself back on Halloween where you throw on your favorite ghost costume, hop on your skateboard, and then push off the wall to go spook some people in the other room. Well, your push on that wall results in the wall pushing on you. That's what causes you to move forward. But there is what we call a force pair here. These forces are equal and opposite to each other. Another example is in the movie WALL-E, when WALL-E turns on the fire extinguisher and propels himself through space. Well, the fire extinguisher pushes on the propellant in one direction, and the propellant pushes on the fire extinguisher in the other direction. It's basically how a rocket works. Using Newton's third law, there's an equal and opposite force. And then the last example, maybe you've had an experience with this, trying to get out of a boat. If the boat isn't tied up anywhere and is just kind of floating there on the water, if you push off the boat, it is going to move one way and you'll move the other way. Your action has an equal and opposite reaction. Well, that force is always the same, but doesn't necessarily mean that the motion is the same for the two objects that are experiencing a force. That's where momentum comes into play. If you have a cannon or really any sort of rifle or firearm, you have maybe heard of or even experienced for yourself this idea of recoil. If you fire off a cannon in one direction, that cannonball has a certain amount of momentum, mass times velocity. And its momentum is usually fairly high because it is usually traveling with a very large velocity, and it's fairly massive to begin with. Well, before you fired, the momentum of that system, the cannon and the cannonball, was exactly zero. It wasn't moving at all, which means that the momentum afterward has to be zero as well. So if this cannonball has momentum going one way, the cannon has to have an equal momentum going in the opposite direction for it to cancel out the momentum of the cannonball. Well, that doesn't mean that it's moving off at the same velocity. That would be crazy. If the cannonball fired one way and the cannon fired the opposite direction in the exact same velocity, you would have two dangerous projectiles. Instead, what happens is the cannon itself has far more mass than the cannonball. And having that added mass means that it can achieve the same momentum quantitatively, the same magnitude of the momentum with a much smaller velocity. So the momentum has to be equal and opposite. Doesn't mean the velocity is. More mass will mean less velocity in this case, and less mass will mean more velocity. So let's look back at our bowling ball toss scenario. Here I'm going to put some numbers to it and say, all right, you're tossing an 8-kilogram bowling ball. And in the process, you plus your skateboard weighing or coming in at a mass of 80 kilograms are going to move in the opposite direction. Well, the bowling ball is going to move pretty quickly. 10 meters per second is how it went out there. You move a lot slower because you have more mass. More mass means less velocity. And we can actually calculate how fast you are moving if you know how fast the bowling ball itself was thrown. So let's look at this example. Before, your momentum was exactly 0 because you weren't moving, the bowling ball wasn't moving. But then you toss the bowling ball at a velocity of 10 meters per second. We can calculate the momentum of that bowling ball, mass times velocity. The mass is 8, the velocity is 10, to give you a momentum of 80 kilograms times meters per second. There's that weird unit again. Well, that 80 kilograms times meters per second is the momentum of the bowling ball. But in order for the total to be 0, the momentum of you plus the skateboard going the opposite direction has to be equal to that. So mass times velocity going one way has to equal mass times velocity going the other. And we know that your mass is 80 kilograms. So the only unknown here is your velocity afterwards, because you know 80 kilograms meters per second on the right has to equal 80 times v, which means that v has to be 1 meter per second, which is why that animation showed you moving so slowly, because you're moving at 1/10 of the speed of that bowling ball. And the larger the difference in the mass, the larger the difference in that velocity is going to be as well. So this is an explosion where you move in opposite directions, and the momentum either cancels out or at least results in the same momentum as before. For the record, you could have been moving with the bowling ball ahead of time and still thrown the bowling ball one direction. It would just be a little bit different because your momentum beforehand isn't 0. So it's still total up to be whatever that initial momentum was. All right, let's look at another example here. Now in the hit and bounce scenario. So here we have a basketball just chilling here, minding its own business, and a bowling ball rolls along at 10 meters per second and bounces off the basketball. Let's see that one more time. Notice here this bowling ball is transferring a ton of momentum to that basketball. It moves a lot faster than the bowling ball was moving to begin with because it is way less massive. But notice how it didn't remove all of the bowling ball's momentum. It still has a velocity here afterward. So that is going to become important in our analysis of this. So let's look at this initial scenario. We've got a bowling ball with a mass of 8 kilograms and a velocity of 10 meters per second, and a basketball, mass of 2, velocity of 0. Our before scenario, if we add up the momentum before for both of these, is the bowling ball is 8 times 10, and the basketball is 2 times 0. So all of the momentum is coming from that bowling ball. The basketball doesn't have anything to contribute to the system. Well, then they hit, and then we end up with a scenario that was shown in that animation of the bowling ball, that 8 kilogram bowling ball, traveling still at 2 meters per second, and the basketball now with some velocity travel off the screen pretty quickly. So we can calculate what v has to be if we plug in for the after scenario r2 momentum. 8 times 2 is plus 2 times whatever v is the total momentum afterward. I can simplify that down. 80 plus 0 is equal to 16 plus 2v. Subtract 16 from both sides and divide by 2. I end up with v equal to 32 meters per second. So that is a ton of velocity that the basketball gained. But in the process, your overall momentum is still 80. Just 8 times 2 plus 2 times 32 will give you a total of 80, just like 8 times 10 plus 2 times 0 equal to 80. In this scenario, both of these velocities are always moving to the right, so everything was positive. But that doesn't have to be the case. In our second hit and bounce here, you'll notice that some of these objects are moving in the negative direction, moving to the left. So I've got a red block here and a yellow block, different mass. Ooh, and then they hit each other. Nice. Let's see that entrance again. Notice how the yellow block is moving at a negative velocity, and the red block was positive and is now negative. Well, I gave you in that scenario 3 of those velocities, but not the velocity of the yellow block afterward. So let's look at this, simplify it out. Here we've got before, it's our 12 kilogram block moving at 8 meters per second to the right, and our 18 kilogram block moving in the negative direction to the left at negative 4 meters per second. So before, if I want to find the total momentum, I just take 12 times 8 plus 18 times negative 4. Those negatives are actually important here. Then after, that 12 kilogram block is moving at a negative 5.5, and 18 is moving at some velocity v. So my after total momentum is 12 times negative 5.5 plus 18 times v. Well, I can plug in those values, and I end up with the red block having a positive 96 momentum, the yellow a negative 90 or negative 72. So overall, there's an overall momentum to the right still. Then I've got negative 66 plus 18v. I add these up, then add 66, divide by 18, and I get a final velocity v of 5 meters per second. Now this velocity can be found because we were able to find the total momentum before and set that equal to the total momentum after, and the only unknown was one of those velocities. All right, for our last example here, we're going to look at a hit and stick. So now we've got this 18 kilogram block just hanging out here on the table, and we fire a 12 kilogram block at it. But notice something different happened here, is instead of them bouncing, they stuck together, and then they're moving together at some unknown velocity. So let's look at what the numbers tell us for this hit and stick problem. Our before is we have this 12 kilogram block moving at 4 meters per second. We say that's a positive because it's moving in the positive rightward direction. And this 18 kilogram block is moving at 0 meters per second. It's not moving at all. So before, we have 12 times 4 plus 18 times 0. There's no momentum coming from the yellow block. Then our after scenario, they are stuck together with some overall velocity of v. It is much easier for us to look at this scenario and think of it as one object rather than two, because ultimately, like, what's the difference? They're one block that's moving together. So instead of saying 12 and 18, let's just put them together and say that that overall mass is 30. So this is one 30 kilogram block that's moving at some velocity. Its momentum has to equal the momentum of the before, which all came from the red block. So after, we have 30, the mass, times some unknown velocity. Well, 12 times 4 is 96, 18 times 0 is 0, is equal to 30 times v. Solving for v, we get 1.6 meters per second. So you'll notice in that simulation or in that animation, it was moving a lot slower afterward because there's so much more mass to equal the same overall momentum. One final situation that I want to talk about that kind of connects us back to our discussion of kinetic energy from the previous couple of videos is this idea of elastic versus inelastic. Now, this is a word that you are familiar with, but probably not in this context. So there are categories of collisions that can define how an object is transferring its energy. So this first example of elastic is a collision where kinetic energy is conserved, where you could do the exact same analysis, but instead of looking at momentum, you're just finding the energy of all the system components before and after, and you'll find that the overall energy is conserved, that no energy was converted away from kinetic. Now that is actually pretty uncommon. That only really happens on like a molecular scale because most situations are at least in some form inelastic collisions, where the kinetic energy is not exactly the same before and after because some of the energy was transferred to heat or sound or light. There's usually a lot of losses in some sort of collision. This scenario here is like a perfectly inelastic collision where there is no bounce at all. A perfectly elastic collision is they're bouncing, not losing any of their overall kinetic energy. In both of these cases, though, momentum is always conserved. So you can always look at momentum and figure out that it is conserved, so the momentum before and after is always going to be the same, but that is not always true for the kinetic energy of the object. So let's look at an example just to compare this difference between the momentum conservation and the energy conservation. Here we have a toy rail car of mass 2 kilograms traveling at 6 meters per second collides with another rail car of mass 3 kilograms traveling at 4 meters per second in the same direction. So basically, one is moving this way, and then the other one is moving faster and collides with it. If after the collision, these two trucks become joined together, what is their resulting velocity? Well, even without a picture or animation of this, we can look at what the before scenario is going to be. This toy rail car has a mass of 2, velocity of 6, plus the other one is a mass of 3, velocity of 4. So my before momentum looks like this. My after momentum, these train cars couple together and then move off in the same direction at the same velocity, which means that I can look at it as one object with a mass of 5, 2 plus 3, times whatever the velocity is of that object. So that outcome turns into 12 plus 12 is equal to 5v. So I can find that the velocity of that final object is 4.8 meters per second. Now, let's look to see, is this an elastic collision where the kinetic energy is conserved, or an inelastic collision where some of the kinetic energy was lost due to other forms of energy? To do that, we're going to do the same analysis, only instead of comparing the momentum of every part, we're going to look at the kinetic energy of every part. And kinetic energy, you'll remember, is 1/2 times the mass times the velocity squared. So looking at my two train cars beforehand, 1/2 times the mass of 2 times the velocity 6 squared plus 1/2 3 times 4 squared is equal to the overall kinetic energy afterward, which is, I added that up here. That is 60 joules of energy total beforehand, which means that if it is elastic, my momentum after, or my kinetic energy afterwards, should also be 60 joules. If it isn't, it means that I lost energy due to something else. So now I know that my final mass is 2 plus 3, so 5. And my final velocity we just calculated was 4.8. So 1/2 times 2 plus 3, 5, times 4.8 squared gets us 57.6 joules. That is an inelastic collision because there was some energy that was lost. It lost about 2.4 joules to probably sound, heat. Maybe there's some light in there, but most likely it's heat, maybe a little bit of sound, that some of that energy was dissipated to something else. So we call this somewhat inelastic because the conservation of kinetic energy does not hold true. All right, with all of that, the main takeaways here, you should be able to define and calculate momentum. P is equal to mv. You should be able to use conservation of momentum to solve for the missing variables in some linear collision, specifically for the process of an explosion, hit and bounce, or hit and stick scenario. And then you should be able to describe this difference between elastic and non-elastic, or elastic and inelastic. And then tell me, if it is non-elastic, how much energy was retained and how much energy was lost due to friction, so heat energy or sound energy.